Hello viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about rocket nozzles. So let's dive right into it. Well, first we have to understand what exactly is our need. Basically, what do we need this puppy to do? First, you have to understand what is the core requirement of a rocket to get off the ground. That's the first requirement, is that it has to burn the maximum amount of gases in the minimum amount of time. Basically, the shortest interval it can do that. So think of it this way, how your car, the more efficient it is, the longer it can stretch your propellant tank, basically your fuel tank. Rockets are kind of invert. Basically, it gets higher efficiency if it can burn through its propellant very faster rate. So instead of liter per minute, we go swimming pool per second. So that's the whole reality of it. Like, it has to do it quickly. Another aspect is how fast your exhaust gases are, that controls your efficiency. Total system efficiency is directly controlled by how fast these puppy go, and of course your also final velocity also. And this nozzle, what does it actually do? Like, if you have to simplify it, like, what the heck do you do? It's basically takes chemical energy and turned it into kinetic energy, and that is very critical aspect, because if you don't have this, you just have a fancy flamethrower, you do not have a rocket engine. So that's the whole point of it. And depending on the nozzles, you will basically design the whole rocket around it. Basically, you could have a scenario where you have one nozzle for second stage and 9 nozzle in same diameter for first stage. So nozzle controls everything. So you could have a skinny rocket that has 9 engine, and you can have like a basically ginormous rocket with only 5 nozzles. So nozzle defines everything about the engine, and this is the main thing, because this is what taking your chemical energy and making your rocket go sky. So let's understand the geometry aspect of it. Now, be very mindful. This puppy is the actual rocket science. Till this point, like if you try to understand turbo pump, they're just turbochargers on supercharger. So there is nothing too fancy about it. Fuel tank, while they are complicated, but any person who is dealing with LNG or even normal road truck size, yeah, it's kind of same kind of architecture. This puppy, there are very few things even touching this, because even if you think, hey, what about jet engines? Most jet engines generally only have conversion nozzle. They do not have convergent and divergent nozzle. So this puppy is on a whole different level. So that's the whole point. It takes insane amount of mathematics. So even if we technically had good everything else, basically rocket engine, we had uglier nozzles, our rockets were not getting very high efficiency. So this is very critical aspect. It requires a lot of mathematics. Now, mass flow is the key, because if you take this nozzle and you will you will read it, hey, it takes subsonic, make it supersonic. Yeah, that's not how it works. Like, if you put this puppy on normal things, which many YouTubers have done that for, like, let's say compressed air equipment or some other things, it does not work, because mass flow is not matched to it. So if you match the mass flow, awesome. Now, what does matching the mass flow means? Think of it this way. This is a pipe. You have your burning stuff here, and then you have normal stuff here. Now you're burning at insane amount of it. That's the whole point of turbocharger. So let's just go YOLO and let's call this 1000 psi. Kind of low, but you get the point. Like, you have 1000 psi. What about atmospheric, sea level, or like vacuum? That's like 15 to 0. So let's just assume 1% here. So what will happen inherently is just your stuff from here want to go there. That's the whole point. Like, pressure wants to equalize. So convergent and divergent nozzle has a throat. Now that throat causes a choke point. Now that choke point is the main thing here. Without that choke point, it's not gonna work. And if you do not have proper choking of your propellant, it's basically hot exhaust gases, is not gonna work. So that's the whole point. This convergent divergent nozzle does that. So what does this choking this mean? Think of it this way. You are burning enough stuff here, so you're getting a lot of hot gases here. What does that mean? That simply means there is a lot of chemical energy in format of molecular vibration. Basically every molecule here, basically every carbon dioxide molecule, every basically water vapor molecule that's here is vibrating a lot of physical vibrations are there, but they are random. They're not going to move your rocket. You want to make all those random vibration is like in one direction. It's like everything go. So this pipe is letting you do that. Now this curvature, that first curvature that is helping you to achieve that, it's like slowly forcing. Basically, if you have this puppy at very sharp basically sharp angle, where it's like directly here, if you put the throat too close to the burning point, it will has a consequence of basically it will not be very efficient. What does that mean? That simply means it will end up creating too much heat in this area rather than actually getting a velocity. And you want velocity. You are not creating a heat engine here. You want velocity. You want kinetic energy, not thermal energy. So you want this to be optimized. The optimization is solely focused on one thing. It's just get as much basically random vibration going into same direction. Now that choke point that you are creating here, what does choking actually means in this context? In this context, it means it reaches sonic speed, aka Mach 1. Now you will start with a burner and all you will have is less than Mach. If at the choke point, if the mass flow is correct, you will achieve basically Mach 1. Now here's the interesting part. The moment you reach the divergent part, basically where it's expanding again, at that point in time, if everything else is working properly, you will end up supersonic. Now till this point it's good, but like you may be like, hey, sonic speed is not that high and rocket has to go to orbital velocity, so how the heck that's going to achieve that? Well, here's the interesting part. The sonic velocity, aka Mach 1, changes based on environment. Now at this point in time, where you have gg amount of high temperature gases, gg amount of gases itself, like not only the temperature is, the amount of gases are also high, the speed, basically the Mach value itself is much higher. So instead of let's say 3 to 400 meter per second, you could have 1700 meter per second. That's a lot of speed, and that's just Mach 1 for this puppy at the choke point. And once you expand it, depending on design, depending on geometry, depending on flow, you could achieve as high as 2 to 3x. Let that sink in. So basically you will start at this velocity, multiply this puppy by like 3 or 4 times. That's how fast you can get your exhaust. So basically this whole thing is acting like a transformer. So same way a transformer can take a basically low voltage and make it bonkersly high voltage, but it will compromise the ampere. Same thing is happening here. You start with ludicrously high pressure. You are having like GG turbo pump fueling this whole puppy as like, liquid oxygen, liquid methane is going all bonkers in. You have just high pressure because there is so much thermal energy. That energy, chemical energy, is being dumped here. It has insane amount of pressure and you keep feeding it, so it will go there. Now what will happen there? It will have ludicrously high velocity. You went from sonic to supersonic here, so you have GG amount of velocity. You could have very high exhaust gases velocity. However, there is no free lunch, so pressure goes down. So your pressure could go lower than atmospheric pressure. Now there is a very easy way to see whether the rocket exhaust is below 15 psi or not. Is simply because if you look at the nozzle and you are seeing the plume is like folding inwards, it has basically less than 15 psi. That's how easy it is to see. It's like if it's going inside, less than 15 psi. If it's going outward, it's more than 15 psi. So that's all this geometry allows us to do. And that's why, like, when you're talking about jet engine, because it does not have the insane amount of mass flow, it does not have the ability to choke that. So the diverging nozzle there would not do much unless you're talking about scram jets or ram jets. And even in those will be like very, very minimal. There is a reason why rocket engines are rocket engines. And rocket engines are optimized for mass flow. They're not designed for like basically, because the mass is limited and you have to burn through it all. Its only sole job is get the most amount of oomph out of most least amount of kilograms that I'm burning, basically the amount of propellant, because it carries its own oxygen also. It does not have the luxury of like optimizing in other ways. Just like burn this through as quickly as possible. So this is what we are talking about here when we are talking about convergent divergent nozzle. And if you truly want to understand the core mathematics, I have provided enough video down below that should give you more than enough understanding. Now, once you are talking about actually having that sonic flow, you're still talking about a nozzle that has things coming out of it. Now, there is a shockwave whenever like high-speed things interacts with low-speed thing. Now, where that shockwave happens, that defines whether your rocket goes upwards or goes boom. So that's a very critical aspect. Now, how do you achieve maximum efficiency? Is there any magical number? Thankfully, yes. That magical number is basically your exhaust pressure must match the ambient pressure. So if your rocket engine is that nozzle, if you put a psi is measuring 15 psi, you are running optimally at sea level. Now let's say you are firing this rocket, let's say second stage rocket, and it's firing at let's say 10 kilometer up, and at that point the psi is 8 psi, and you want to go horizontally rather than vertically. You're like, okay, 10 psi. If your engine exhaust like bell point is registering 10 psi, awesome. So that's how we can achieve perfect efficiency. Consequence of that is our atmosphere has a very weird gradient. Basically most of the 15 psi at the sea level, so your rocket will start at 15 psi. Very quickly it will reach 10 psi, 8 psi, 5 psi, 4 psi. Very quickly it goes into almost vacuum. So that's the whole point. Basically the whole atmosphere, in less than 100 kilometers of travel, vertical travel, you will end up going from 15 psi to 0 psi. And you might say, okay, there is still some stuff in upper atmosphere that is like around 100 kilometer above Kármán line. It does not equate to even 1 psi. So if you are below 1 psi, it generally stops being accounted for. So, and because of the engineering, because of the geometry, you can only fine tune all these things for 1 psi, one exhaust flow. So you have to make a decision. Now you may be like, okay, let's optimize for the basically high altitudes. You will think that because again, rocket will spend most of its time in higher altitude rather than lower one, and it will go from higher to 0 psi much quicker, much more delay wise, rather than if you divide it in two segments, 15 psi to 8 psi, 8 psi to 0 psi, 8 to 0 will take much longer. So you will be like, oh, let's optimize for that long run. run. But you cannot do that. If you did that, let's say you took a Saturn 5, like let's optimize this engine for that kind of psi, 8 psi, let's just say, the shock wave that will be created, it will end up as we call overexpanded structure, and in those sort of scenario the shock wave will travel inside the engine bell, and in that engine bell you could have what we call wall separation. Basically your gases are no longer flowing from the wall and they will split from the wall. This is what we call wall separation, and it will hit back. Now that could cause oscillation if you are lucky, or worst case scenario goes boom. So that has happened. We have learned this the hard way, that we cannot go overexpanded too much. Slightly overexpanded we can manage that, but not too much. So generally whenever you look at the rocket launch, instead of seeing a basically absolutely 90-degree plume, you'll see a plume, a little bit of taper. That means it's like running around 14 psi or something like that. So that's the lowest we can do that. We want to go lower, but reality is if it goes boom on the launch pad, there is no point. So this is like the sacrifice that we have to make. At least it has to get off the ground, and you can easily see that from Saturn 5. Like once it starts to go higher altitude, it's like expanding too much because the psi was too damn high. It's expanding too much, it's wasting too much energy, like energy laterally is being wasted rather than pushing directly. But again, that's a compromise. It has to get off the ground. If it does not get off the ground, it goes boom, there is no point. So that's the whole thing. So basically the rockets are generally slightly overpressured. Now we want to do overexpanded, but slightly is the what we can manage. And you can easily notice that in space every rocket is underexpanded. The reason for that is you have to achieve 0 psi at the nozzle end. You cannot achieve that. You fundamentally cannot. You need an infinite size nozzle. You cannot achieve 0 psi. So at that point in time, basically whenever you are designing a nozzle that's supposed to work on 0 psi only, everything else becomes a primary factor. It's like, how big of a nozzle can I physically fit? That's the step number one. Some rockets have actual extender stages. Again, not very efficient because it adds extra complexity. You do not want that. So you're like, okay, this is the mass limit I have, like this much, let's say 300 kilograms. That's how heavy my nozzle can be. Okay, then you will start to figure out what kind of diameter I can make it. Like again, if it does not fit inside your interstage, there is no point. So there is other limitation, because inherently we want 0 psi, but it is unachievable. So we make compromises based on other things, because again, even if you made a nozzle that is huge, bonkersly huge, but consequence of that nozzle itself is so heavy that is wasting your efficiency. Was the point. So there is always a stability curve that we have to aim for, and you have to sacrifice here. There is no it can do everything. You have to sacrifice. So this is one thing that you have to understand. Exhaust pressure is the key factor here. And if you watch anything in a scenario where you have slightly overexpansion or very lot of overexpansion, you will have a scenario where shock diamonds are created. Now be mindful, shock diamonds are only created in atmosphere. They are never created when you are at upper atmosphere. So once you go upper atmosphere, your rocket will not have marked diamonds. I have no idea why the heck Star Wars nowadays have marked diamonds on vacuum space. It's like Rogue One, it was like you can see shock diamonds, like it's in vacuum. There cannot be shock diamonds. Shock diamonds are happening basically your exhaust while it's coming out at very high velocity. It does not have 15 psi. So atmosphere is like nope. Now the moment atmosphere does that nope, it goes hot up, so it has more energy. At that point it fights back to the atmosphere. It's like nope, and then atmosphere is like nope. So tuk, you get around 3 or 4 marked diamonds easily. But that does not happen in high altitude, and let alone in vacuum. That does not happen. I have no idea which is the CG artist that did that. So that's the whole thing you have to understand. Stability is key. If your rocket goes boom, there is no point in it. Now let's understand the material aspect of it. Now this is very high pressure, especially at that throat. If you want to figure out which place in your rocket is going through the maximum amount of stress, that's that place, throat basically. It has very high pressure and very high temperature. If you have to cool anything, you have to cool that. If you have to make something robust, you have to make that. That's the soul of a rocket basically. Now it has to have very high wear resistance. You have to understand that you are talking about a blowtorch, and blowtorch can cut through stones. So you have to design something that can handle that over long period of time. Now I'm like, hey, 8 minutes is not long enough. Find me a metal that can withstand 8 minutes of blowtorch. Even tank armor can be cut at that point in time. So you have to design something that can manage that. Now copper, niobium and steel alloys are generally chosen. Generally copper and niobium are the whole option. Copper is like the primary. Most of the time things are made out of copper, and sometimes, especially in basically SpaceX Merlin upper stage, they use niobium. The simple reason is it does not have any cooling. So it has to cool through black body radiation. It just has to get hot and radiate through infrared radiation. So it has to it has to withstand very high temperature while retaining structural integrity, because if it starts to become weak and starts going happening, the rocket will become uncontrollable. So they have to use that kind of alloy. Consequence is expensive AF. So generally for lower stage they use basically copper systems. Now abrasive nozzles are used if you want to do this on budget. Basically if you want to use normal cheap steel stuff, you can coat the inside using graphite, and graphite will wear away slowly, burn away and wear away, and it will protect your system. Benefit: cheap. Side effect: it's use and throw. So this is what we are talking about material. So most of the time you have to design a system that can manage the mass flow rate that you are dealing with. Now cooling becomes a critical aspect, because you are talking about a blow torch and it will cut through anything. So how the heck you cool it, that's up to you. Again, you can just have a sacrificial layer like generally used for solid boosters, or even sometimes disposable low grade rockets where they have just burn the nozzle away. It's like don't think too much about it. Benefit: it's cheap. Side effect: it's not very efficient, and it's very inefficient, and not to mention it's single use. So do not even think about making a reusable rocket. And the reason why it's inefficient, because it's thick. It's inherently thick. You are inherently putting 2-3 inches of material that's gonna wear away. So inherently it's not a good idea. However, you may think like, okay, what about active cooling? Actively cooling it with fuel. Now you may be like, why the heck you want to cool it with fuel? The problem is, if you want to cool it with oxygen, while it will work on principle, it will work, there is a serious risk that you already have a metal that will react with oxygen, and you have a lot of oxygen and you have a lot of heat. The stoichiometric ratio you already have. Basically you have heat, oxygen and material to burn. You really do not want to take that risk. Can it be done? Yes. Physics is not saying that. It's just that engineers are like, yeah, let's not do that. Let's just not do that. So even in Merlin or other scenarios, you will generally have kerosene running through. In case of space shuttle, you will have oxygen running through. In case of Raptor, you will have methane running through, because we are like a bit more comfortable in those sort of scenario. And those puppies will be running at very high mass flow rate to keep the heat away. Otherwise the throat will simply melt, and you have to maintain perfect geometry here. So this thing has to be cooled at idiotic rate. Basically, if I'm not mistaken, Merlin engine could have like around cooling capacity, like the amount of heat that is waking up with the kerosene, it's around 10 megawatts of heat. So it's bonkers amount of chemical energy is being dumped here, and you have to absorb that. There is no other way to make this thing light otherwise. So that's how it's done for cooling. However, you have to understand that because these channel pipes are so thin, basically so many of it, like you could have like a fuel path that is like in meters or hundreds of meters, you will require a lot of pressure from your turbo pump. So your turbo pump, without this, let's say you are using ablative nozzle, you'll be like, your turbo pump 2000 horsepower, be good. If you try to add cooling system, you have to build a turbo pump that can provide much higher pressure. So around, let's say, instead of 2000 horsepower, it will go to 2500 horsepower. So you can push all this through, because if that puppy fails, your engine will fail. Now other times, especially if you're talking about really huge engine, physically huge engine, as an F1 engine, it had that kerosene cooling, but because the nozzle was so huge, if they did this structure to till the end of the bell, it would be too goddamn expensive to build, and again it will also add mass. So they realized something very interesting. Cool is a relative term. So they are like, what if we cool this puppy using the exhaust gases from gas generator? Gas generators are designed to run on an unbalanced fuel. Basically they have too much oxygen or too much kerosene depending on the design, and they are always unbalanced. So at this point, inside the chamber, 3000 degrees Celsius. At the basically gas generator exhaust, they are generally at much lower temperature. We are talking only calm, low, freezing temperature of 300 to 600 degrees Celsius. So some engineers like, hey, 600 degrees Celsius, that's nothing for steel. So what we're gonna have is basically we're gonna have a pipe that directly comes from the gas generator, and so we're gonna what we call film cooling. So basically those exhausts are running through, and that's why when you see the footage of Apollo, you will notice the engine is there. Engine is awesome. Then you have this dark film, and then you have GG brightness. Why the heck you have GG brightness here, not at the throat? Simply because that area is being film cooled. Basically cold gases are protecting it. So that you have 3000 degrees Celsius, then you have 600 degrees Celsius, and then you have steel, and steel is like 600 degrees Celsius. I can do this all day. So that's how we are achieving cooling on F1 engine. And this is a very tricky aspect, because again, everything has to be balanced. It's like, if it costs too much, you're not going to build it. If it takes too long to build it, you're not going to build it. So F1 engine was kind of very interesting utilized, because it has to be huge, bonkersly huge, to utilize both of them at the same time. So that was surprisingly awesome. And sometimes you will find, especially in small rockets, they put water in the fuel just to make sure the combustion temperature is low enough. So cooling is a very serious deal. So this was my presentation about basically engine nozzle. I hope you liked it, learn from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.